Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. Welcome to the 11th clip. As you know, continuous maps are good carrier of convergence sequence, compact set, connected set, in the sense that continuous maps carry convergence sequence to a convergence sequence, compact set to compact set, connected set to connected set. And though you have seen in BSc that continuous functions are not a very good carrier of Cauchy sequence, that is, continuous maps are unable to carry a Cauchy sequence to a Cauchy sequence in general. Today we will see another failure of continuous maps, that actually we will see that continuous maps are unable to carry a locally compact space to a locally compact space. For this, let's begin with an example. Okay, consider the identity map. Consider the identity map I, the set of rational numbers, to set of rational number. Okay, here let me consider the topology on the domain as the discrete topology, okay, where domain Q is discrete space. We are considering discrete topology on this domain Q, and the codomain Q is the subspace. Of R with usual topology. Okay, so here we are considering the discrete topology, that is, every subset of Q is open, and in the codomain we are considering the subspace topology induced by the usual topology on R. Okay, so it is not discrete. Okay, and we have discussed that every discrete space is locally compact, and we have also discussed in some previous clips that the Q as a subspace of R is not locally compact. Okay, fine. Okay, here the image of this domain Q is Q, because identity map, it is defined as I x equal to x for all x in Q. So I Q equal to Q. So this Q is this, and this Q is this. So this is discrete, and this is subspace. This is subspace of R. Fine. Okay. So this is discrete. So this is locally compact. This is subspace of R. So it is not locally compact. Okay. But this function I, the identity map, is continuous because its domain is discrete. Any function whose domain is discrete is continuous. We have discussed several times, and that's why every sequence is continuous, isn't it? Every sequence has domain n as a subspace of R. So n is discrete. That's why every sequence is continuous. We have discussed several times. In the same way, since I has discrete domain, so it is also continuous. It is very easy. If you take any open map here, its inverse image will be a subset of Q. Since every subset of Q is open, being the topology is discrete, so inverse image of every open set is open in this discrete domain. So I is continuous. This I is continuous. So this is a continuous map whose domain is discrete, so locally compact, but the range is not locally compact. Fine. So image of a locally compact space under a continuous map is not locally compact. Okay. Fine. So continuous image of a locally compact space may not be locally compact. Now the question is, what kind of maps are good carrier of locally compact spaces? Okay. Actually, if we add some more properties of a map to the continuity of it, then we will see that it will be a good carrier of locally compact space. So let's prove a result. This result says that continuous open maps are good carrier of locally compact spaces. That is, if a map F is continuous as well as open map means if image of every open set is open, okay, under this F. So if F is a continuous as well as open map, and if this X is locally compact, okay, so X to Y, this is a map, then this Fx, this image as a subspace of Y, it will be locally compact. This result says this. Okay. Continuous open image of a locally compact space is locally compact. Okay. Proof is very easy. So proof or case of the proof. Case of the proof. Okay. So let F X to Y this be a continuous open map. Continuous open map. Okay. Our claim is continuous open map and the space X and this X domain. X is XB locally compact. Okay. So our claim is Fx as a subspace of Y. Subspace of Y is locally compact. Okay. Fine. Okay. So we have to show that every point of Fx has a neighborhood base consisting of compact sets. This is the definition of locally compact space. Fine. So for let Y be any point of Fx, okay, and V be any neighborhood of Y. Okay. Next, choose a point X from F inverse Y. Okay, so this is say X, this is Y, F is this. Okay. Say this is Fx. Okay, so we have taken any point Y from this Fx. Now we are considering F inverse Y. Now this function F may be many to one, so this F inverse Y may be a subset of X, may not be singleton. So this F inverse Y is a subset of X. We are taking any point small x from this F inverse Y. So Fx is Y. Okay. So in this way we are getting a point X in capital X ultimately. Since this capital X is locally compact and F is continuous, okay, and B is a neighborhood of Y, this B, this B any neighborhood of Y. So F inverse B will be a neighborhood of X. How? B is a neighborhood of Y, so there is an open set O containing Y, okay, which is totally contained in V. Okay, so F inverse V will contain F inverse O, and F inverse O will contain F inverse Y, and X is a point of this F inverse Y, isn't it? Now O being open in Y, so F inverse O, because F is continuous, so F inverse O is open in X, so this is open set in X containing small x and totally contained in F inverse V. So F inverse V is a neighborhood of small x in capital X. Okay, fine. Okay, So since X is locally compact and F is continuous, F is continuous, the F inverse V is a neighborhood of X, and for this neighborhood F inverse V of X, since X is locally compact, so for this neighborhood F inverse V of X there exists a compact neighborhood by the definition of locally compact space. So every point of small x, every point small x of capital X has a neighborhood base consisting of compact sets. Neighborhood base, so this being a neighborhood of small x in capital X, so there is a compact neighborhood of X totally contained in F inverse V. This is the definition of neighborhood base. So there exists a compact neighborhood N of X such that this N is totally contained in F inverse V, and actually this means F of N subset of V. Okay, now we can write this. We know Fx is y, and since n is a neighborhood of x, so x is in n, so fx belongs to fn, so this y belongs to fn. Not only that, actually y belongs to fn interior. Okay, why? Just let me explain this. N is a neighborhood of x. It is a compact neighborhood of x, so neighborhood of x. So N being a neighborhood of x in capital X, so there exists an open set, say O1 containing small x, which is totally contained in N. So fx belongs to f of okay, so x in O1, this. Now we know interior of a set is the largest open set contained in the underlying set. So x in O1, it must be contained in an interior, and this is a subset of N. This is the largest open set contained in N. This is the largest, and this is also an open set contained in N, and N not is largest, so this inequality will happen. Okay, so this fx belongs to actually f of n naught, and is a subset of fn. Okay, so f of n naught subset of fn, which is a subset of v. Fine, good. Now here is the where we will use the fact that the map F is not only continuous, it is an open map. That is, it maps every open set to open set. Since F is an open map, if n naught is open in Y, because n naught is open in X interior, so if n naught is open in Y. Fine. So if n naught is open set in Y, containing Y, and totally contained in V. Okay. Fine. What is Fn? Fn is compact, because n is compact, F is continuous. This is continuous image of a compact set is compact. So Fn is compact. So Fn is a compact set. It contains an open set containing Y. So Fn becomes a compact neighborhood of Y. Okay. So this Fn is a compact neighborhood of Y such that this Fn totally contained in V. What does it mean? What does it mean? It means if we consider collection of all compact neighborhoods of Y, it will be a neighborhood base of Y consisting of compact sets. Okay. Why neighborhood base? Because for any open set V, for any neighborhood V at the beginning of this sheet, this VB any neighborhood of Y. So for any neighborhood V of Y, we are getting a compact neighborhood of Y totally contained in V. This is the definition of neighborhood base, isn't it? So we are getting a compact neighborhood of Y totally contained in this V. So if we collect all compact neighborhoods of Y, then it will form a neighborhood base of Y consisting of compact sets. And hence we have taken Y from Fx, any Y from Fx. So Fx becomes locally compact space. Okay. Okay, so let me write this. So collection of all compact neighborhoods of Y forms a neighborhood base. Okay, at Y consisting of course compact sets. Okay, hence this Fx is locally compact. Okay, so continuous open image of a locally compact space is locally compact. Continuous image of a locally compact space may not be locally compact, but if we add the openness to the continuity of the function f, then we see that it will become a good carrier of locally compact space. Fine. Now one application of this result today we will discuss that already we have seen that local compactness is not productive, isn't it? We have seen R omega with product topology or box topology, not locally compact. Okay, though we know R with usual topology is locally compact. So product of locally compact spaces may not be locally compact. So local compactness is not productive property. Actually, it is not even countably productive property. Okay, but we have actually discussed at the beginning of the discussion about local compactness that R, Rn, in particular C, all are locally compact spaces. So Rn, locally compact space. So finite product of local compact space is local compact. From this we can at least guess, Okay, so we will generalize this now. Actually, okay, let me take a new page. Okay, so result. This result says that a topological product or a product space, this product of x lambda, lambda and capital lambda, so every x lambda topological space, okay, this is a Cartesian product and we have considered here the product topology, okay, then it is called product space. X lambdas are factor. So a product space this is locally compact if and only if every factor of it, that is every x lambda here, every factor of it is locally compact, among which all but finite number of factors are compact, among which all but finite number of factors are compact. Okay, so this is a topological product of topological spaces x lambda, lambda and capital lambda. This topological product will be locally compact if and only if every factor x lambda is locally compact, and among all this x lambda, all except finite number of x lambdas are compact. Okay, fine. So proof, in this case the proof. Okay, first let me prove the easier part. So let x equal to product this x lambda, lambda and capital lambda, this be locally compact. Okay, fine. And we know we know that projection maps are continuous and open but not closed. Okay, we will use this. Since projection maps are continuous and open, so just the previous, by using the previous result, the image of this X under each projection map will be locally compact, because this X is locally compact. Image of a continuous open map, image of a locally compact space under a continuous open map is locally compact. Okay, so projection maps are continuous open. So if we apply projection map on this X, then the image will be locally compact. Since this, so pi lambda X, that is X lambda, this is locally compact for every lambda in capital lambda. Okay, so every X lambda is locally compact. Fine, every X lambda is every factor locally compact, and we have to show now that among these X lambdas, all except finite numbers or X lambdas are compact. Okay, fine. Now let for some point X, this is of the form X lambda of capital X. Since capital X is locally compact, so every point of it has a neighborhood base consisting of compact neighborhoods. So this point will have at least one compact neighborhood. So let for some point this in X, okay, N be a compact, N be a compact neighborhood of small x. For some point this N be a compact neighborhood, okay, of it. Fine. So N is a neighborhood of X in capital X, and capital X is product space. So there exists a basic open set containing this small x and totally contained in this capital N. So there exists a basic open set. Basic open set B, we know the basic open set in product space looks like this. Product B lambda, lambda in capital lambda, where these B lambdas are open in X lambda, and all but finite number of B lambdas are whole X lambda, that is B lambda equal to X lambda for all lambda except say lambda 1, lambda 2 dot lambda k, say. Okay, so there exists a basic open set B such that this X belongs to this B, and this B is totally contained in N. So therefore pi lambda B subset of pi lambda N. Okay, look at N What is N? N be compact neighborhood of this point X. Okay, this is important. Fine. So pi lambda be this. Now B is product this B lambda. So pi lambda B means B lambda. So this implies B lambda subset of pi lambda N. It is for all lambda. For all lambda, any pi lambda I can use here. So for all lambda in capital lambda. Okay. So this implies x lambda subset of pi lambda n for all lambda not equal to, look at this, when lambda not equal to this, then b lambda equal to x lambda. So not equal to lambda 1 lambda 2 dot lambda k. Okay, and x lambda cannot be a proper subset of this. Okay, this implies x lambda equal to pi lambda n for all lambda not equal to lambda 1 lambda 2 dot lambda k. Now n is compact neighborhood, so compact, and pi lambda projection map continuous. So this is continuous image of a compact set, so compact. Okay, so x lambda becomes compact. So since n is compact and pi lambda for every lambda in capital lambda, these are continuous. So pi lambda n equal to x lambda, these are compact for all lambda not equal to lambda 1 lambda 2 dot lambda k. So x lambdas are compact except this. So, and there are finite number of indices. Okay, so all x lambda except x lambda 1 x lambda 2 dot x lambda k are compact. All but finitely many factors x lambda 1 x lambda 2 x lambda k are compact. Okay, so this is the easiest portion or easier question of this. So this result says that a product space this is locally compact if and only if every factor of it is locally compact, among which all but finite number of factors are compact. So first we have shown that this every factors are locally compact, and then through this we have shown that all x lambda except this finitely many factors are compact. So among which all but finite number of factors are compact is also done. Okay, so now we will assume that we will assume now that every factor of this product is locally compact and all but finite number of factors are compact. Okay, then we will show that this product is also locally compact. Okay, so next part, it is also not tough, it is also easy. Okay, fine. Okay, just let me arrange the pages. Okay, so converts part. Let x lambda in capital lambda, this be a family of locally compact spaces, and among them all except finite number of members are compact. Say except x mu 1, x mu 2 x mu k, except this all others are compact. Okay, we will show that their product is locally compact. Okay, consider their product. Consider their topological product. That is, consider the Cartesian product of the underlying sets and consider the product topology on the Cartesian product. Okay, this is topological product. Consider their topological product x equal to this product x lambda in capital lambda. Fine. We will show this product x is locally compact. That is, we will show that every point of it has a neighborhood base consisting of compact sets. Okay, so here I have to share few things like this. In order to show that every point has a neighborhood base consisting of compact sets, we have to take any point x first from this capital X. Okay, then we have to take any open set, isn't it? Any open set, say U in capital X, or any neighborhood U of X, any neighborhood, and then we have to find a compact neighborhood, isn't it? We have to find a compact neighborhood N of X is totally contained in U. Okay, so we have to start with any neighborhood of any point of this capital X. Now U being a neighborhood of this small x, so there exists an open set, say O, containing this x, totally contained in U by definition of neighborhood, and the open set in this x, that is in product space. Now O being open set in this product space, so there exists a basic open set. There exists a basic open set B containing x contained in O, and O is totally contained in U. Okay, now if we show that for this basic open set containing x, there exists a compact neighborhood N of x which is totally contained in B, then this N will be totally contained in U automatically, isn't it? So if we start with any basic open set containing x And if we show there exists a compact neighborhood of X totally contained in this basic open set, then this will be done. That's why we will consider just any basic open set, because we know how the basic open sets in a product space looks like. We know, isn't it? Fine. Got it? Okay. So consider the topological product this. We will show now this X is locally compact. Fine. So you have to take any point small x in capital X, and instead of taking any neighborhood of that point, we will take any basic open set containing this point X, and we will find a compact neighborhood of that point X totally contained in this basic open set. And if we are able to do this, and we can declare that this X is locally compact as discussed here, isn't it? Fine. So let X obviously will be of the form this, being a member of this. Let X in this, and B basic open set, so of the form this, B lambda lambda in capital lambda, this. We have to write this where these B lambdas are open in X lambda, and this B lambda equal to X lambda for all lambda not equal to, say, lambda 1 lambda 2 dot lambda n, say. Nothing new. This says that this X belongs to B. Okay. Therefore, X lambda belongs to B lambda. Okay. X belongs to B. X belongs to this product. So lambda coordinate of this point will be in the lambda factor of this product. You know from school, you know this. Okay. So we are getting two sets of indices here, lambda 1 lambda 2 dot lambda n, and here had the page gone. Just a minute. Okay, it is here. This X mu1 mu2 mu k. Okay, so we have two sets of indices, no? Mu1 mu2 mu k, these are also in capital lambda, and lambda 1 lambda 2 lambda n, these are also in capital lambda. Okay. Okay. Now let me take their union of the two sets of indices, lambda 1 lambda 2 lambda n, and this mu1 mu2 mu k. Okay. So let this, we take union of these two sets of indices, and both are finites, mu1 mu2 up to mu k, lambda 1 lambda 2 up to lambda n, both are finites. So after taking their union, we will get again a finite sets. Sum of mu1 may be sum of mu's, maybe sum of lambdas. Okay, so the number may not be k plus n, it may be reduced. Okay, so after taking their union, we will get ultimately a finite subset of this capital lambda. So we can again rename them as xi1, xi2, isn't it? So let xi1, xi2 dot 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 xim, this equal to this union of this first mu1, mu2 dot 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 mu k, this union this lambda 1, lambda 2 dot dot lambda n. Okay, obviously m is less or equal to k plus n, set theoretic. Okay, fine. Now every factor this x is this product of x lambda, every factor x lambda is locally compact, but we will not consider all the factors. We will consider the factors x xi1, x xi2 up to x xim. Okay, okay, others are actually compact. Look at this, others are compact. Okay, the xi1, xi2 up to xim covers whole this mu1, mu2 up to mu k, as well as all of this lambda 1, lambda 2, lambda n. Okay, so this covers this lambda 1, lambda 2, lambda n, as well as mu1, mu2, mu k. So if we consider x xi1, x xi2 up to x xim, other than this, all are compact. Okay, fine. And since everyone is locally compact, so x xi1, x xi2, x xim, these are also locally compact. Fine. Since x xi I equal to 1 to n, this are locally compact. I am not saying that others are not locally compact. These are locally compact. Okay, so since these are locally compact, okay, we have taken x from the product, whole product x, product of x lambda, lambda n, capital lambda, and x is of the form x lambda, lambda n, capital lambda. No, so the coordinate of x in this x lambda x xi is small x xi. Coordinate of x in this capital X lambda is small x lambda. So coordinate of this x in capital X xi is small x xi. Okay, so small x xi is a point of capital X xi. Right? And since this capital X xi is locally compact, choose compact neighborhood. They locally compact, so at least one compact neighborhood of this small x xi will be there. So choose compact neighborhood. Okay, compact neighborhoods, say n xi of small x xi such that this n xi totally contained in b xi. look at this. Every xi is locally compact, and small xi is a point of this locally compact space, and this bji is a jith factor of the product capital B. This capital B, this capital B. Okay. Okay, so this is an open set containing this xi because x in B. Fine. So this is a neighborhood of this xi. Since this is locally compact, so every point of it, so for this xi, it has a compact, it has a neighborhood base consisting of compact sets. Neighborhood base consisting of compact sets. So it has a compact neighborhood, okay, totally contained in bji, and let it be nji for every I 1 to n. So since xi these are locally compact, choose compact neighborhoods nji of xi such that this. Okay, then consider this product n equal to product in lambda in capital lambda, where n lambda equal to x lambda if lambda not equal to ji. Okay, if lambda not equal to ji, where I equal to 1 to n. Okay, otherwise means if lambda equal to ji, then nji already defined. Okay, so we got nji1, nji2 up to njm, and other than this we have defined n lambda, x lambda. Okay, now so if lambda not equal to ji, then x lambda, so now lambda not equal to ji means not equal to this mu1, mu2, mu k. Okay, so x lambda, if lambda not equal to this, x lambda is compact at the beginning, this, except this x mu1, x mu2, x mu k, all others are compact. Okay, not this means it cannot be this. Okay, fine. So here if lambda not equal to ji, then n lambda equal to x lambda, and these x lambdas are compact. And if lambda equal to ji, then also nji are compact neighborhood. So every factor here is compact, so this n is compact. Okay, then this is a compact and neighborhood. Compact neighborhoods nji is a compact, you can check very easy, compact neighborhood of x. This is a compact neighborhood of x, and this n, this nji1, nji2, njm contained in this bji1, bji2, and all others are whole set. Okay, so n contained in B. Got it? If not, just I am repeating once more. So N is this product in lambda, lambda in capital lambda, and B is this product B lambda, lambda in capital lambda. Fine. First consider the xi1, xi2 up to xm. N xi1 subset of B xi1. Look at this. N xi1 subset of B xi1. So this N xi1 subset of B xi1, N xi2 subset of B xi2, N xim subset of B xim, and all others are here whole set x lambda, here also whole set x lambda, isn't it? So this. So every basic open set B containing X, for every basic open set B containing X, there exists a compact neighborhood of X totally contained in this basic open set. Okay, and this implies, as we discussed, this implies X has a neighborhood base consisting of compact sets. Compact sets. So this product capital X, this product of X lambda, this is locally compact, and we are done. Okay, so we got that a product space, this product X lambda, is locally compact if and only if every factor of it is locally compact, among which all but finite number of factors, except finite number of factors, all others are compact. So from this statement of this result, we can conclude that finite product of locally compact space is locally compact, and that's why Rn locally compact, but R omega is not locally compact. So note is this finite product of locally compact spaces is locally compact. That is local compactness. Local compactness is finitely productive. Okay, so let me stop here for the time being. So in the next clip we will discuss another kind of characterization of locally compact Hausdorff space, and that will open a new chapter called compactification. Okay, so for the time being, goodbye. Thank you. Keep watching.